Let's take a look at procedural versus object-oriented programs. On the left here we see a procedural program, a main program with the data structure exposed in the code. The dog data structure has a name, a weight, and a favorite toy. Separate from the main program is a dog library, which would have procedures and functions to carry out various behaviors, like make a toy its favorite or compare two dogs. However, you'll notice that if we change the structure of the dog, if we were to add a new piece of data, for example, maybe its height, we'd have to make the change here in the main program, and we'd have to recompile the main program and every program where a dog is being used. However, changes in the dog library would not necessarily cause a recompile of the main program. This modularity is an aspect of procedural programs. Object-oriented programs leverage that to a greater degree. Here in the main program for an object-oriented program, we see that we have my dog, which is an object reference to an object in memory. We send it the message fetch and tell it to fetch a squeaky toy. Once it's fetched the squeaky toy, we can tell that my dog object to make that squeaky toy its favorite. How does this work? Well, the behavior of the object, fetch, get name, make favorite, and compare, if you will, the procedures and functions, are stored along with or defined along with the name, weight, and favorite toy, the structure itself. We combine the data structure, name, weight, and favorite toy, and the behaviors into a single structure that we call a class. So a class acts as a template that defines both the behavior and the data structure for that object. At runtime, when the main program creates a new MyDog object, that object is created with a name field, because name is in the class, and a weight field because weight is defined in the class, and a favorite toy field because favorite toy is defined in the class, and the object has a pointer back to the class so it knows what its behavior will be. In this case, my dog is called an object reference. It's like a pointer to the object in memory. So the main program does not have direct access to the internal state of the object. It simply sends messages to the object, and the system makes sure the messages are carried out. So access to an object would include access to its data and its behavior as well. So when I access my dog and tell it to fetch a squeaky toy, then a message is sent to this object to fetch, and the fetch code would get executed with the toy that we pass it. And then if we said my dog and pass the message make favorite a squeaky toy, it'll set squeaky toy to be the favorite toy for that object. We see here that maybe later in the program we have another object called your dog, which again is a dog object and would have a name of Maddie, a weight, and a favorite toy, which might be a chew toy. Also notice that there are different classes for the squeaky toy, chew toy, and ball. Squeaky toy would have data of like volume and sound and behavior of play. Chew toy would have a flavor as a type of data and play as a behavior, and ball would have a color and play. So notice that any toy that we use would know how to play even if the behavior of playing is different. Here we see two objects, one that has the name Bowser and one that has the name Maddie. What do these objects have in common? Well, they're both types of dog objects. They have the same attributes of name, weight, and favorite toy that describes their internal state, and they would have the same behavior. They could tell you their name, you could compare one dog with another, you could make a certain toy their favorite. They have the same basic behavior. So when we see objects that have the same attributes and the same behavior, we would say they belong to a common class, and that's the term that we use, and then we would use the class to design what the object will look like. So at design time, we would specify what a dog should have. We would say, based on our application, that our dog needs to have a name, a weight, and a favorite toy, because that's the way we're going to work with the dog in the application. So at design time, we use the class to specify what the object should look like, but the object is created at runtime. We create a specific instance of a class at runtime, and we call that an object. You can have many different objects. As you see here, we have two separate physical objects, but they're all considered a dog class, part of the dog class. Examples. You could see, for example, the definition of a table in a database is like a class. It defines what the table can hold, and each row would represent an object, for example, a specific instance in that table. If you had a table of orders, then the table would have things like order number, order date, etc., and then each row would have the specific values for that specific order. Or a recipe, for example. When you're creating a recipe for a meal, the recipe describes what you're going to do and what you need to create that meal, but the meal is the instance. The recipe is the class, if you will. You can use that over and over to create new meals. The meal is actually what you create at the time. That's the instance of the recipe, if you will. Same thing with blueprints and buildings. The blueprint is done at design time to design what the building will look like, and when the building is constructed, we can create an instance of that blueprint, if you will, and that's the built building. Also, like an integer defines what the behavior and what the internal state of a number would be. 23 would be an actual instance of that number. And actually, in object-oriented systems, you will see that integer itself is actually a class, and 23 would be considered an instance of that class. So then, what is a class? A class is a template or a factory for creating new objects. The class defines the name of the class, in this case dog, and it describes the attributes. The variables are internal state values, in this case name, which is a string, the weight, which is a number, and a favorite toy, which could be some type of toy. It could be a chewy toy, squeaky toy, a ball, or some other type of toy. And it also has the definition of the messages that that class can understand. For example, a dog would know how to get its name, and a dog could make a toy its favorite. Now, in this case, we use the term class, and we do this at design time. But at runtime, we're going to notice that the object will understand the message. For example, if I go back for a moment, we have two object instances here created based on the dog class. If we send the message getName to this object, it will return the value Bowser as a value for its name. If we ask this object getName, it will return the value Maddie. So we have two different objects, both of which are types of the dog class, but at runtime they're separate physical objects, they have separate memory structures, and therefore can contain separate values for the attributes, even though the attributes are the same. So then what is an object? Well, at runtime, an object is created in memory. It is the object that holds the values, and it is the object that does the work for us at runtime. Classes are there to tell the computer what type of memory structure to create. So memory is allocated for its attributes, and here's an example of Java code that will actually create a new dog object. Now over on the left, we're saying we need an object reference called myDog, which will point to the new dog object, and myDog is of type dog. In this case, we're seeing that myDog is of type dog. Java is a strongly typed language, and we have to define what type of object reference must be. Then over on the right-hand side, we create a new instance of the dog class, in this case, a dog object, and using the new keyword, and assign that to the myDog object reference. So at runtime, when new dog is executed, then the computer will look at the dog class, see it needs to create a data structure in memory that has a name field, a weight field, and a favorite toy field, as you can see down here. Give it the values that it's supposed to get, however it does it, which we're not going to talk about here. And now we create an object reference, the line that you see here, and that is now being pointed to or being used by myDog to reference that object. So now if I send a message to my dog, or in Java terms, call a method, like getName or makeFavorite on myDog, it'll go ahead and execute the code. So each object has a unique object reference, a pointer to that object in memory, and each object has a pointer to its class definition. So the object stores the data structures, and the class definition stores the actual code. So we see there's some similarities to procedural code, right? We see that the procedural code is here in the dog class, and we have a separate data structure, but the big difference is the data structure is not in the main program. Notice that if we change the definition of the dog class and add something like height, then that would cause a recompile of the dog class, but would not necessarily cause me to recompile my main program. And that's a huge benefit of object orientation. So how does this work in Java? Well, over on the left, we've defined a couple of different classes. We have a dog class. Don't worry about the syntax of public and class and all that. We'll get to that in the Java code. But we see here a dog class, and a dog class has an attribute of a toy, which would be, well, we're going to reference it as my toy, and a favorite toy. So a dog could actually have a couple of different toys, its toy and even its favorite toy. Maybe this is the toy that it's playing with. And we can see that it has a method called fetch. Fetch would take a toy and then say to that toy, I want to play with you, and then maybe make it its favorite toy. Down here we see a chew toy class, which has a play method. Here there's the code to play with a chew toy, and here we have a public class squeaky toy, which would have the code in order to play with a squeaky toy. Notice both chew toys and squeaky toys have the same behavior, the same method play, even though the code is probably different. The benefit of that comes about when we look at the program itself. Over here we have a public program. We have a program called dog tester, and inside that program we start by creating a new dog object, and the myDog variable object reference points to that dog object. And now we create a new chew toy. We create a new chew toy object, and we store the object reference for that new chew toy object in the cToy object reference. Now we can say to the myDog, fetch cToy. Now the dot notation here is Java notation for basically sending a message. We're telling the myDog object to fetch, and we're passing it cToy. So what happens is the object reference myDog, which is pointing to an object of type dog, then executes the code for fetch. Fetch is over here. We pass in cToy, and therefore that specific object will take in that cToy and fetch that toy. Here we create a squeaky toy, sToy, a new squeaky toy, and now we can tell myDog to fetch sToy. And we can go on and on from there. So once it fetches sToy, it plays with it and makes it its favorite. For example, at the end of this code, the favorite toy for myDog is what? It would be a squeaky toy, because we've replaced this chew toy that we set to be its favorite toy here through fetch with the squeaky toy through the fetch here. That might be a little bit involved, and we'll go through that as you go through the actual code examples and the class itself. You'll see more and more of that work. So when the toy receives a play message, it executes its play behavior. Depending on the type of toy, different behavior may be exhibited. So notice that here I can tell it to fetch cToy, and it'll automatically tell that toy to play, and that toy, let's say in this case a chew toy, will execute the code for a chew toy. But if it happens to be a squeaky toy, we're reusing the same code, passing a different object, in this case the object reference for a squeaky toy, and we're reusing the code, and automatically we get the behavior for a squeaky toy without having to make any changes or write any if statements or things like that. That's something we call polymorphism, and that's something we're going to take a look at in the next lesson. So in part 2 of this, we'll look at some of the principles of object orientation. We'll look at abstraction, which is where we define what behaviors and what data we need to keep about a specific object. We'll look at encapsulation. How do we make sure that the methods and behaviors and the variables of a class are kept separated and hidden from other users of that class and objects, so that changes to the implementation of the class do not break the applications that the users are using. We'll also look at inheritance. Inheritance is a property of object-oriented systems. Here, for example, we can see that dog is part of an inheritance hierarchy, inheriting attributes and behaviors potentially from an animal superclass. So all animals, for example, would have a name, and all animals can speak, although dogs, bears, and snakes may speak differently. And we can even see that dogs can actually be broken down into subclasses like Poodle and Great Dane. Now, I don't know that this is the best example of a subclass, and we did this to make you think about it. Can you think of any attributes that are different for Poodles and Great Danes? Name, for example, would not be a difference. Both Poodles and Great Danes would have names because they're types of dogs, and dogs are types of animals. And we said animals have a name, and therefore all the subclasses of animal would inherit the name as well. This is one of the benefits of object-oriented systems, making it easier to reuse data and code among related classes. So the only thing I can think of is maybe the amount of curl in their fur, or how curly it is. So poodles are very famous for being curly type fur, and maybe Great Danes not so much. Now, part of analysis, as we'll see later, and part of abstraction, as we look at our problem domain, is to say, Poodle and Great Dane are really not actually subclasses of dog. But on the other hand, if poodles speak very differently than Great Danes do and need different types of behavior, that could be a way of doing it. We would say, okay, all animals can speak. Dogs, therefore, can speak. However, poodles speak very differently than how Great Danes speak. Again, this is pushing the example a bit, but you could see that we could actually leverage common behavior and also have different behavior for the subclasses. So the last thing is for polymorphism. And polymorphism is the ability of different objects to get the same message and react or respond differently. So we could say speak now to a dog and it'll say woof, or a duck would say quack, or a snake would say hiss, or a bear would growl. So in summary, we've seen how to define an object, a class, an attribute, a method, and a message, and we've explained what it means to create an object-oriented application. Thank you.